Okay, let's finish up. We have learned about Newton's second law, the sum of the forces equals ma. It is the most fundamental equation in all of physics. So it's here to stay. And again, this is the summation symbol. The sum of the forces equals ma. So you know whenever there's been an acceleration observed by an object, you know a force has caused it. And if ever there is a force, you know it's going to cause an acceleration of an object with a given mass. So let's talk about the units again. Well, we just said that the unit for force is the Newton, and its abbreviation is N, capital N, and it stands for kilogram meters per second squared. For in the English units, it's a slug foot per second squared, which is the pound, abbreviated LB. All right, there's lots of other units. Anything that has a mass, a distance, and divided by a time squared would be a legitimate unit for force. And in the English system, mass is in slugs. You could have any unit for distance divided by time squared. So some other possible units could be, let's think of some. How about a gram, like following this pattern? How about a gram kilometer per minute squared? So that shows this pattern, and it is a legitimate unit for force. Not a common one, but it is a possibility. You could have gram centimeter per second squared, and that is an actual unit for force. It's called the dyne, D-Y-N-E, so it is an actual unit. However, we're not going to use it much. So, in the English side, we could have had a slug, and then an inch over hours squared. So again, following the same pattern, a unit for mass, distance divided by time squared. So be aware that there are other possible units. These are the common ones that we will use. All right, let's do our first problem using our new formula. So sketch a man, and he is pushing a rock, so he is applying a force to the rock. He's accelerating the rock 0.12 meters per second squared, and the mass of the rock is 4.2 times 10 to the fourth grams. And the question is, find the force that the man is exerting on the rock. Find the force. Alright, so to do that, we pull out our basic equation. The sum of the forces equals ma. In this case, we're only considering one force. So I'm going to drop the sum of the forces and just call it F equals ma. And I'm going to put in what I know. I know the acceleration. It'll go in for A. I know the mass. And I'm going to change the mass because I want to work in kilograms. Because up here, we learned that a kilogram meter per second squared is a Newton. So I want kilograms in this problem, not grams. So I'm going to change my, well, right there I wrote it as, I took out the scientific notation and wrote it as 42,000 grams. But I'm going to change the decimal 3 to the left, and that will give me the kilogram measure. So I end up with 42 kilograms times 0.12 meters per second squared, and that will come out to 5.0 kilogram meters per second squared, which is the Newton. And that is the force this man is applying to the rock to cause it to accelerate. Again, force and acceleration go hand in hand. If a force is exerted, there will be a mass. I'm sorry. There's always a mass. When a force is exerted, they will always cause a mass to accelerate. And if there's an acceleration of a mass, you know there's a force involved. So, all right. Finishing up these ideas for today, I want to make note that weight is a force. Because up here, we said that a pound was a unit for force. So therefore, pound is weight. Newton is not our common way of describing weight, but Newton is also a force. A weight, these are both can be considered as weights. So weight is a force. So when I'm talking about the one force being weight, F equals ma, I can rewrite that. Instead of putting F here for force, since weight is a force, I'm going to put a weight here equals m, and the acceleration on any object on planet Earth is going to be the acceleration constant for gravity, g. So of course we know on planet Earth that's 9.8 meters per second squared, or 32 feet per second squared. So weight equals mg, where g is the gravitational constant, depending on which one we need for the given situation. So let's find a man's mass who weighs 151 pounds. This is a common physics question. So find the man's mass who weighs 151 pounds. So I'm going to grab my formula, weight equals mg. And let me turn the paper over. Dramatic pause. You can go ahead and work ahead of me. Alright, so we have the man weighing 151 pounds. And I'm grabbing the weight formula, weight equals mg, which came from F equals ma. It's just a specific case of that. And I'm putting in 151, because that is the weight. I'm asked to find the mass, so m is what I'm looking for. G, since I'm working in pounds, I know I'm in the English system where we're in feet per second squared, 32. Dividing both sides by 32, I can find that the mass of the man is 4.7 slugs. That's the unit for the lovely unit for mass in the English system. Alright, in the US of A, 4.7 slugs is the mass. Alright, let's find the mass of a man who weighs 672 newtons. Alright, so similar process, it's just that we're working on the metric system now. So I'm going to pull out the units, the formula weight equals mg. So the mass of the man who weighs 672 newtons. Remember, this is a force, weight is a force, so under weight, I'm going to grab the number 672, and g is 9.8. I'm going to divide both sides by 9.8, and I'm going to get to 2 sig figs. The mass of the man is 69 kilograms. So, how much? Now let's go to the other direction. Let's say we have a mass given. Sorry, my stand isn't very steady tonight. How much does a 4.7 slug man weigh? So we have a man in America who has a mass of 4.7 slugs, and I want to know his weight. So I pull out weight equals mg. This time I'm looking for his weight, and I know his mass and g. So his mass is 4.7, and g is the gravitational constant, and that's 32. And I'm going to get weight is 151 pounds, sig figs 150 pounds. The next question is, what machine measures mass? I know I can hop on any scale and find my weight in pounds, but pounds is a weight, and what if I want to know what my mass is? What machine will I go to measure mass? Well, to be honest, there really isn't one. It turns out that even in chemistry class, when we put our chemicals on our triple beam balance and we have that little tray to measure the mass of some things, actually the scale has basically figured out the weight and converted it to mass, similar to what we did mathematically. So it's set up mechanically to make that conversion. So there really isn't a good answer to this question. Now there are situations where we take water and take a container, fill it with water, and we put a mass into the water. We can observe how much the water level changes and calculate the mass that way. But there isn't an easy machine that can measure mass. It's all weight converted to mass, similar to what we did in the problem here, where we were given weight and asked to find mass. All right. And an interesting thing about mass is it's the same everywhere. So everything I've written in this video, anything I've written on the paper goes on your notes, and mass is the same everywhere is a particularly important note. What is, not that. This is the important note. Mass is the same everywhere. And that means whatever your mass is on Earth, it's the same on the Moon, Jupiter, in the next galaxy. So mass is the same everywhere. Mass is how much is there of you. How much is there in the object in question? The mass is the same everywhere. So let's say that with that in mind, that will help us answer this question. Suppose an object weighs 3.42 times 10 to the third pounds. Find its weight on the Moon. Now to answer that question, you do have to know the gravitational constant for the Moon, so I'll give you that. The Moon's gravitational constant is 5.3 feet per second squared. So if you want to drop an object on the Moon, it will accelerate 5.3 feet per second squared compared to our 32 feet per second squared on planet Earth. To answer this question is two parts. So the first part, I'm going to grab my formula, weight equals mg. Weight equals mg. And I have been given the weight of the object, but since weight changes from here to the Moon, but mass doesn't, so I'm going to get the mass of this object on Earth. Then I'm going to go over to the Moon and use that same mass to find the weight, the new weight on the Moon. So let's find mass first. So grab your weight equals mg equation. You're going to look for mass. You put the weight, 3.42, that's 3 times 10 to the third. I'm going to write that without scientific notation. 3420, mass, and g is 32. Then I'm going to divide both sides by 32, and I get 110 slugs is the mass of the object. So moving over to the Moon, so this is always a two-step process. So the first step is to find mass. Then we're going to go over to the Moon and pull out weight equals mg. And this time we know the mass, and we're looking for the weight on the Moon. So we're going to use mass, which was calculated on this side, the 110, and the new acceleration constant, 5.3 for the Moon. And we multiply that and use sig figs to get 580 pounds. So something that weighed 3,420 pounds on Earth end up weighing 580 pounds on the Moon. So good weight loss program. Go to the Moon. All right, let's go the other way and we'll call it a day. All right, the object on the moon weighs 580 pounds. Let's calculate what does it weigh on Earth. Again, this is a two-part question. So we're going to go and take the information on the moon, because that's what I have. I have weight equals mg. I'm given the fact that it weighs 580 pounds on the moon. So this is the moon side. And the weight equals mg, 580. We're going to look for mass, because the mass will not change when we go over to Earth. So we're going to use, since we're on the moon, we have to use the gravitational constant of the moon, 5.3, and we divide and we get 110. And since we're working in feet, this is slugs. That's the mass of the moon. So now we're going over here to planet Earth, because that's what the question asked us to do. Weight equals mg. Weight equals 110. That number came from this side. That's the mass we calculated. Times, now we're on Earth, so we're going to use 32. With sig figs, we get 3,500 pounds. All right, those examples and the concepts and formulas that we've covered will help you through your classwork today. So, carry on.